February 2021. GTA Online, the online mode of one of the most profitable entertainment products ever made, took about 6 minutes to load. Not to download, to load. Every single session. And it had been that way for 7 years. Players complained for so long it became a meme. Then, one anonymous player got tired of waiting. He didn't have the source code, so he attached a profiler to the running game, a tool that watches where the CPU actually spends its time, and sat through one more 6-minute load. Almost all of the time landed in 2 places, 2 small pieces of code, and both of them are the subject of this lesson. Culprit 1. The game loads a 10 megabyte file describing about 63,000 purchasable items and parses it with repeated calls to a C function called sscanf. Here's the trap. On many systems, sscanf starts by measuring the length of its input by walking it byte by byte to the very end. Every single call. So parsing token number 1 scans all 10 megabytes. Token number 2, all 10 megabytes again. 63,000 tokens, each one rewalking the entire buffer. Culprit 2. After parsing each item, the game checks whether it has already seen that item by scanning a plain array of everything seen so far, one entry at a time. Look at the loop. Item 1 checks 0 entries. Item 60,000 checks nearly 60,000 entries. Add it all up, about 2 billion comparisons. To deduplicate a list that almost certainly contained no duplicates at all. The fix was embarrassingly small. Measure the string length once and remember it. Replace the array scan with a hash set where asking, "Have I seen this?" costs the same tiny amount of work no matter how many items came before. Load time dropped by 70%. Rockstar confirmed the diagnosis, shipped the fix, and paid him $10,000 through their bug bounty. Now, here's the part that matters for us. That code was not written by fools. In 2013, when the item catalog was small, it was fine. Nobody can feel the difference at small inputs. The cost was growing with the catalog, quietly, every time a new car or weapon was added, and nobody had priced the code in the right currency. This lesson is about that currency. The obvious way to measure code is a stopwatch. Run it, time it. But the stopwatch answers the wrong question. It tells you how fast this code ran, on this machine, with this compiler, at this input size, while Slack was doing whatever Slack does in the background. Change any of those, and the number changes. Worse, the stopwatch can't warn you about the future. That loading code would have benchmarked beautifully in 2013. So instead of seconds, we count steps. And we count them as a function of the input size, which we call n. The model is deliberately crude. Every basic operation costs exactly 1. An addition? 1. A comparison? 1. Touching any spot in memory? 1. It's called the RAM model. And hold on to that last assumption, because at the end of this lesson, we're going to break it. Let's count something. Here's a function that sums an array, written in the pseudocode this course uses on screen, so the ideas stay language agnostic. One step to set total to 0. Then the loop runs n times, and each pass does a couple of steps. An add, a store, one final step to return. Total, something like 2n plus 2. Now, you could argue with my tally. Does the loop's own bookkeeping count? Is an assignment 1 step or 2? And that's the first real lesson here. The exact count is not stable and not interesting. What's stable is the shape. Double the input and the cost doubles. Sum is a straight line in n. Now a real problem. Does this array contain a duplicate? The honest first attempt. For each item, compare it against every item after it. 2 nested loops. The inner loop runs about n times for each of the n outer passes. Total comparisons. N times n minus 1 over 2, roughly n squared over 2. Watch what that means. Double the input, and the cost quadruples. That's not a line, That's a parabola, and it's exactly the shape that ate those loading screens. Do something per item, where the something itself walks all the items. Big O notation is the act of throwing away everything about those counts except the shape. We drop constant factors. 2n and 100n are both order n. We drop the smaller terms. N squared plus 50n is just order n squared. Because as n grows, the biggest term doesn't just win, it makes the others irrelevant. At 1,000 items, n squared is 1,000,000, while 50n is 50,000. At 1,000,000 items, n squared is 1,000,000,000, and 50n is a rounding error. Big O answers exactly one question. When n gets large, how does the cost grow? Almost every algorithm in this course lands on one of 6 rungs, and each rung comes from a recognizable move. Order 1. Constant. Touch a fixed number of things, no matter how big the input. Order log n. Have the problem at every step. Order n. Linear. Touch each thing once. Order n log n. Have, recurse, and recombine over everything. That's the shape of good sorting. Order n squared. For each thing, touch everything. And order 2 to the n. For each thing, the work doubles. Learn the moves, not the symbols. Once you can see the move in the code, the rung reads itself. Abstract ladders don't build intuition, so let's price the rungs in wall time. A modern laptop core does on the order of 100 million simple operations per second. Take 1,000,000 items. Log in about 20 operations. Unmeasurable. Linear, 10 milliseconds. N log n, 1/5 of a second. N squared, 2.8 hours. Sit with that gap. Between linear and quadratic, at 1,000,000 items, sits the difference between 10 milliseconds and nearly 3 hours. No compiler upgrade closes that. No faster CPU. Hardware buys you constant factors. The shape of the growth is fixed by the algorithm. And that is why this is the first lesson of the course. The strangest rung deserves a closer look. Logarithmic cost appears whenever each step halves what's left. Take 1,000,000 items and keep halving. 1,000,000, 500,000, 250,000. 20 halvings and you're down to 1. 1,000,000,000 items? 30. Growth so slow it barely registers as growth at all. Whenever a structure in this course manages to halve its problem each step, you'll see log n show up in its price tag. And Lesson 8, Binary Search, is built entirely out of this one move. Here's a wrinkle, the simplest search there is. Walk the array, return the index the moment you find the target. What does it cost? It depends. If the target sits in slot 0, 1 comparison. If it's missing entirely, n. Same code, costs 1,000,000 apart. So the cost isn't one number, it's 3. Best case, target first. That's trivia. Nobody plans around getting lucky. Worst case, target absent. That's the number Big O quotes by convention, and for a good reason. The worst case is a guarantee. It never costs more. You can build systems on never. And the average case, what typical inputs cost? For this search, about half the array. For most of this course, worst case is the only number we track, but one giant exception is coming. Hash tables are beloved precisely because their average case is constant, while their worst case is linear. That story is Lesson 12. Now for the most misunderstood word in this lesson's title. Some operations are occasionally expensive, by design. The classic example, appending to a dynamic array, a list in Python, an array in JavaScript, a slice in Go. The array owns a block of memory with some capacity. Appending into spare capacity costs one step. Write the value, bump the length. But when the capacity runs out, the array allocates a new block, twice the size, and copies every element across. That append costs n. So which is it? Is append constant or linear? Watch what the doubling actually does. Start at capacity 1 and append 8 items. Copies happen when capacity grows from 1 to 2, 2 to 4, 4 to 8, 1 plus 2 plus 4, 7 copies total. Append 1,000,000 items, and all the copies ever performed still sum to less than 1,000,000. The doublings get more expensive, but they get exponentially rarer. The sum stays under 2n. Total cost of n appends, under 3n. Spread across n operations, about 3 steps each. That spread out price is the amortized cost. And notice it's a guarantee about the sum, not a hope. Picture every cheap append depositing a couple of spare tokens into a bank, and the rare, expensive copy withdrawing the balance. The bank never overdrafts. Now, any single append might still be slow. In a game's frame budget, or real-time audio system, those spikes matter, and you'll reach for structures with worst-case bounds instead. But over any run of appends, the structure is fast. By arithmetic, not luck. Everything so far? Price time. Memory gets the same treatment. Space complexity counts the extra memory an algorithm needs, beyond the input itself. Our 2 duplicate checkers make the trade concrete. The nested loops use 2 index variables and nothing else. Constant space, quadratic time. The hash set fix remembers everything it has seen. Linear space, linear time. Neither one is free. They're trading different resources. And spending memory to buy time is the single most common trade in this course, and in production engineering generally. One source of space cost likes to hide: recursion. Every nested call holds its variables in a stack frame until it returns. Recurse n levels deep, and you're holding n frames of memory, even though no line of code ever allocates. Lesson 9 makes that stack concrete. Time to break the promise. The model assumed every memory access costs the same one step. On real hardware, that is false, and not slightly false. A read that hits the CPU's nearest cache costs about 1 nanosecond. A read that misses every cache and goes all the way to main memory? About 100. Same instruction, 2 orders of magnitude apart, depending only on where the data lives. The consequence? 2 algorithms with the same big O can differ by 10x in practice, depending on whether they touch memory in an order the hardware likes. And this is also the honest answer to when constants matter. When n is small, real sorting libraries switch to a quadratic sort below a couple dozen elements because its constants are tiny. And when memory layout makes one algorithm step physically cheaper than another's. So here's the discipline for the whole course. Big O first. Always. No constant factor survives that wall timetable. Then, with the shape settled, the machine gets a vote. Next lesson is that vote. What caches actually do, and why arrays are the hardware's favorite data structure.